Okay, everyone, so we're going to officially get started. Our guest speaker is from Mao Materials. She's got some really cool stuff. I mean, they got some really cool stuff that they're doing. And you're going to really appreciate this because she's not boring. She's full of energy. So I'm going to go ahead and turn it over to Schauer Gimenez.
Thank you very much. Thank you all for having me here today. I do want to step back in time just slightly to when I was in 7th grade, and I actually did a science fair project that was called "Which of these items are biodegradable?" Little did my 7th grade self know that that's actually what I would be studying in my career now. So it's weird how something in 7th grade can really kind of excite you enough to make it your long career when you're much older than 7th grade. So I've always been really fascinated about the environment and materials and how we could maybe rethink materials. So fast forward a little bit to college. When I was studying environmental science, I was really fascinated again with what can you do with an environmental science degree? Well, I had a lot of people say, you should be an industrial hygienist. And then all my friends made fun of me and sent me pictures of trees with big toothbrushes. That is not what an industrial hygienist does. We had a lot of people say, you should work for OSHA. And I'm like, I don't really know, that doesn't really sound that interesting to me. And I had one professor say, you should be an engineer. And I looked at him like he was crazy because engineering is scary. There's so much math. And so I was like, do I really want to do engineering? So I actually made the leap. When I got my PhD, I decided to switch to engineering. And this is a photo of about 10 years ago. According to Facebook, I posted it 11 years ago, like yesterday, of me in the lab for my PhD. This was one of those days where a professional photographer came in to take photos of what we're working on in order to impress the university. Well, we laid out all the great work that we're doing. We studied wastewater treatment in my lab, and they looked at it and said, don't you have anything more colorful that we could photograph? So, I don't know if you noticed, but that's a pretty annoyed look on my face. I'm trying to smile, but I was actually really annoyed by the photographer because, no, wastewater treatment is not colorful. It's not awesome, but it's really important for our daily life. While I was doing my PhD, our lab hosts a conference every year. And one year, we actually had a student, her name is Molly Moore, she was studying at Stanford, attend the conference. It's great because, wastewater treatment, there's not a whole lot of females that study it or work in it. So we instantly became friends, mostly because we were the only 2 females at the whole conference. But it turns out that we had a lot more in common than that. We were both studying methane. So methane, potent greenhouse gas, that's found in natural gas, but also generated at wastewater treatment plants, which is what I was studying, agricultural facilities, and even landfills. And now you can use methane for either heating or electricity, which was what I was focusing on, or even to power your own vehicle. But I remember sitting down with Molly and talking about her research versus mine, and she said, you know what? You should really turn that methane into a plastic substitute. And I looked at her and I said, does that work? And she said, well, that's what I'm studying. And I was like, that's fascinating. And I jokingly say that it changed my life, but it actually kind of did. Because as soon as I finished my PhD, I moved away from Wisconsin, where it does look like this for the majority of the year, to sunny San Francisco to help her start the company. And we actually started it with a third co-founder, Allison, who also got her PhD at Stanford. So at Mao Materials, we are focused on turning waste gas streams into eco-friendly biodegradable materials at competitive economics. And here's how we do it. We take methane, and in the form of biogas, and we feed it to a specialized set of microorganisms. Now these organisms convert the methane, carbon from the methane into a long-chain biopolymer. This is a plastic substitute, and it can be turned into many different really interesting products. And the cool thing is once these products are no longer needed, you generally throw them away. They end up at a waste facility, but if they're degraded anaerobically without oxygen, methane is produced, and we can close the loop and create a cradle-to-cradle cycle. It's really changing the way that people think about plastics. We're not recycling, we're biodegrading now. And Mao Materials has a really versatile technology. we can use all sorts of different sources of methane. As I mentioned, it's found in agriculture facilities, wastewater treatment plants, landfills, etc. And we can produce a bunch of different products. Now, because this is a really interesting kind of vast area, we need to focus. So we're really focused on one material in particular, and it's a biopolymer called polyhydroxyalkanoate. I'm going to call it PHA from here on out because it took me about a year to be able to pronounce polyhydroxyalkanoate. And more specifically, our process produces poly-3-hydroxybutyrate, or PHB, which is one type of PHA. And we actually do this through a biological process. We call it bacterial effect because the bacteria actually get larger and larger and larger with the polymer inside of them. So normally you would see a lot of black specks, but we actually have a few white ones. Those white ones are actually the polymer, the granules that form inside the bacteria. And this is because of the metabolic pathway. So most of the time, our methanotrophs want to go from methane, they want to replicate and produce CO2 on a very linear path. But you can give them the right environment for them to switch at the formaldehyde step. Goes through the serine cycle, the PHA cycle, and you're ultimately producing PHA. So they're not using the carbon for replication anymore, they're actually using it as energy storage. If they had brains, they think that they need it later. We never give them the later. So here's a photo of some more of our bacteria, and they do produce it, as I mentioned, inside the cell. So we do have to break open the cell, clean and dry the material. We like to call it harvesting, because that seems like such a more gentle term, but the bacteria are sacrificed in this process. We've only had a few people have issue with that. But they're doing something that's even better than normal. They're actually making an all-natural polymer. And this polymer is super cool because it can biodegrade in many different environments. So there's other biopolymers, bioplastics, maybe like PLA that you're familiar with. Forks and spoons are made out of it. It's fantastic. But it needs high temperature and high pressure in order for the biodegradation to occur. We're lucky here in the Bay Area because we have these facilities. So that's why I believe you guys probably do some compost collection as well. If you have PLA cups, great. Definitely step one for the environment. But what if we switch that cup to PHA? You could actually degrade it in your home compost, at a landfill, at a wastewater treatment plant, or even in the aquatic environments. And now we never advocate for the oceans to be a disposal ground. We don't want everyone just dumping all of their stuff in the oceans. I don't know if you guys have followed, but we're following quite closely all the debris that's being found on random remote islands. How is it getting there? It's getting there by the oceans. What if we switched that plastic to PHA and there were microorganisms in the ocean that would degrade that material before it even got to those remote islands? That's how we see the future of plastics. And so now we've talked a lot about biodegradability. PHA is a thermoplastic, so it technically can be recycled both chemically and mechanically. It would go back into making PHA all over again, but there is no infrastructure. If you had a PHA something, you threw it in your recycling bin, the material recovery facility would probably freak out because it doesn't have a number. It has nothing. It's such small volumes right now that no one has classified it. We imagine that once us and others are wildly successful, there'll be so much on the market, they'll have to give it a number, whether it be number 8 or 0 or whatever it is. We're following closely to make sure that PHA can become a recyclable polymer as well, as there's already that knowledge in people's brain. People know what to do with a plastic, number 1 or number 2, in most places. And now biodegradability is actually different than bio-based, and yet there's a lot of confusion around this. Biodegradability is generally what happens to it when it no longer is needed. Like, for instance, home composting is one type of biodegradation, but a lot of people are like, oh, this plastic is compostable and biodegradable. No, that's the same thing. They're just one type of that. But when you talk about bio-based, actually that means where does it come from? Is it produced from rapidly renewable carbon? And so what we're advocating for are polymers that fall in this upper right-hand corner, that they're both bio-based and biodegradable. Of course, PHA is up there, lucky for us, but there's others as well. The interesting thing is the upper left and the bottom right, they're all called bioplastics. So you could get a bioplastic that actually isn't biodegradable. It gets really confusing really quickly. So we're working really hard with brands and others and consumers to make sure that this terminology gets sorted out so that you don't have to look at a product and be like, I don't know what to do with this anymore. That you're like, oh, it's biodegradable. It goes in my green bin. Awesome. Like, we want to make sure that it's as streamlined as possible. We're a small company. We're not going to change everybody's thoughts overnight, but we want to be part of that conversation to make sure this messaging stays the same. So we're advocating for next generation polymers. We're all used to our first generation persistent plastics made from petroleum. There's so much of it out there. We're all using it. It is fine. It is what it is. There's a second generation persistent plastic made from plants. So this is bio-based, but not biodegradable. There are bio-based and biodegradable polymers that are made from plants as well. PLA is an example. There are other PHAs that are also made from plants, and they're great. They're a next step. But when you have to extract sugar from plants, it's relatively energy intensive, and you're growing a crop to extract the sugar instead of using it for food. So you do have a food versus a fuel debate. The fourth generation is where you have biodegradable polymers made from waste, and this is where Mao Materials fits in. So of course, we're always advocating to get to this fourth generation as soon as possible. So now PHAs, they have what we call a wide design space. And what that means is they're compatible with a lot of other things. So you can add additives to it to make it flexible versus rigid. If you were to look at PHA all by itself, it's inherently brittle. Every PHA paper, especially like in the 70s when it really first came out, says it's brittle, it's never going anywhere. Well, we've been able to have an additive package that's turned it into flexible thin film, or even spun it into fiber. And after I'm done, I do have some samples of some prototypes that we've made that you guys can look at. But with this wide design space opens up the doors for so many different applications. And I get emails every week. Can you make a diaper? Sure. How about a plastic bag? Uh-huh. How about a gift card? Or can you 3D print it? Or packaging? Or, and the answer for most of them is yes. But we're still a small company. But before I let you know exactly what we're working on, I'm going to take a step back and tell you how we got to where we are today. So this is a photo of the three co-founders back in 2011, I believe. We were, again, it was a staged photo. They did not ask us if we had anything more colorful this time, which was good. So as you can see, I'm actually smiling. I'm not giving an annoyed face. But we are outside of the wastewater treatment plant that we work on. And this was our first kind of article. It was written in this Silicon Valley Business Journal. And we were so excited to be featured somewhere because we weren't even really a company yet. It was three of us with a great idea. Three engineers who wanted to start a business, who knew nothing about business, who had to learn a whole new language because there's acronyms in business that we didn't even know existed. Cost of goods sold, COGS. What's a COGS? What? We did a lot of Googling in order to understand what a business plan would be. We luckily were accepted into the Clean Tech Open here in the Bay Area in 2010, and that really was a lot of mentorship and helped us through some of that learnings without having to completely use Google to start our business. We also started writing a lot of grants. We knew we had to pay ourselves somehow, and luckily 2 years later we got our first National Science Foundation grant in 2012, which also meant we could hire our first employee. Tara is in the middle here. She is our first employee. We are very excited about that. We also needed a lab space. So we partnered with the USDA facility that's in the Berkeley area to get some space. We could afford a quarter of a lab. It had one desk, one computer, one chair, and 4 people, which made for some interesting days when we all needed to use the one computer. But it did have a ton of other lab equipment that while Mao Materials didn't own, we could totally use. So in here is a 1 liter bioreactor where we did some of our first experiments outside of Stanford University. And we were very proud of this because we're finally like taking this out of the lab and into another lab, but we're getting there. 2012, we also won the Postcode Lottery Green Challenge based out of Amsterdam. This was really exciting because not only did it give us about $630,000, it gave us a big check, which was pretty cool. We got to walk around New York City with a check like we won the lottery. But it also really kind of helped us decide, okay, what are we going to do? We're actually a real company. We actually have money in the bank. A lot of these people on the top here are advisors. The 2 on each end are advisors that helped us along the way to understand some of that business. And then Freddie, who's next to Molly there, was our first intern. We were very excited because we're like, wait, we're a company, we can actually have interns now. So he was our first college intern, and he actually ended up working with us after he graduated for about 2 years. And then he left us for something else. But it was really exciting to have like, oh my gosh, like we're a real company. We also decided with this money that we wanted to take stuff out of the lab and into the field. So we partnered with Silicon Valley Clean Water, which is the wastewater treatment plant here. It's actually at the end of Redwood Shores. And we basically talked to anyone we could about methane and said, would you be interested in hosting a small project? They have welcomed us with open arms since day one. Not only that, I remember our first meeting when they said, oh, we actually have this shipping container that's been abandoned on site. Could you guys use that? And we were like, yeah, we could totally use that. And so, you know, the Silicon Valley story is everyone starts their company in a garage. We started in a shipping container at the wastewater treatment plant. We feel we have a cooler story. But we were able to take the methane right from the anaerobic digester in the field with no sterilization, and we were able to run a small 10-liter reactor. This meant sampling at all hours of the day and night, and there were still only 4 of us. So I had done a lot of midnight sampling at the wastewater treatment plant, which is a little creepy because it's dark. But we were able to produce grams of this material. We made grams of plastic, and we thought we had made it because we actually produced something in the field. And we had so many people ahead of this say, it's impossible, you're never going to get it to work. So we were really excited about that. With those grams of plastic, we were actually able to make a handful of products. These are we call them our poker chips. They're literally round discs. We made about 6 or 7 of them, and we thought that, again, we were like, this is amazing, now we've made a product, this is great. But nobody wanted poker chips, except for maybe one casino in Monte Carlo wanted like millions of them, which we could not supply. But we were like, oh, at least we could make something and people could touch and feel it. Up here later on, if you have a chance, we're actually at Poker Chip 3.0, I'd like to say, because now we actually have them colored. We can make 50 to 100 of them at a time. We crank these out pretty quickly, just more for prototyping, for people to feel. Nobody really is going to buy these poker chips, but we've been able to make them. And we were at grams of material, and that's great, but we knew we needed to scale. So in 2015, we built our pilot plant. We literally purchased an old pipe, which is the black tall thing, and we built this unit ourselves. So these are members of our team. We're up to like 7 people by now, and we all basically took turns putting things together, undoing something that somebody else did because it wasn't quite right, gluing pipe, wiring. We've all learned so many random skills because we decided it was probably cheaper and better for our knowledge to build this facility ourselves. We built it over in the Berkeley facility because it was indoors. We could control a lot of things. We did a few tests. We then disassembled it and reassembled it at the wastewater treatment plant. So this is now where we're at Silicon Valley Clean Water. And that shipping container that's behind it is the old abandoned shipping container we used to work in, but it now just houses all of the electronics. that's how big we've gotten. This is a fully automated system, which is wonderful, but I get kind of cranky when my team maybe complains a little bit about having to log in at midnight, and I was like, I used to have to go to the treatment plant at midnight. But they can log in and they can fix anything remotely, or they can head in if something is pretty bad. We have not had any sort of big issues yet. We do have two sides of this pilot plant. One side is where the methane or the biogas comes in, and the other side is where the oxygen comes in. Our organisms are aerobic. We keep them separate because methane and oxygen together is potentially explosive. So we do not want that. We have a lot of features on there. For instance, the operators get notified if something is out of range via text from their phone, which I don't get, so I'm happy about that. They also have interesting nozzles that go inside of the pipe or the tank, and that is how the gas gets into the liquid for the organisms to make sure that they get their methane. So it's almost like a jacuzzi system that's inside of there. There's about 500 liters of bacteria that live inside of there, and they produce roughly 10 pounds of polymer every week. When we run it. We do run it in batch right now in order to change things. We're constantly improving and tweaking. It's been down a couple of weeks because we actually need the operators to do some work at our other facility. So they're pretty flexible. But for right now, we can produce a pretty consistent batch when we started on a Monday, and it finishes roughly on a Friday. Once that polymer, those 10 pounds are produced, we do have to break open the cells and clean it and dry it. That all happens at a facility in Emeryville where we've partnered and actually got a grant that paid the ABPDU Advanced Bioproducts Demonstration Unit or something. It paid them directly, but it's under our account. So we basically have a lump sum of money to run tests using any equipment that's in their facility. And they have some really interesting equipment for us to get that polymer out of the cell and clean it and dry it. It's just at such a bigger scale, we stockpile runs, and then we run it over there every so often, every couple of weeks. And then once we get that cleaned and dried polymer, we do a lot of testing on it. So we have a bunch of different pieces of equipment that actually happen to be at the USDA facility because they have a bioproducts group. So all of these photos here are actually Mao Materials employees using equipment that is technically not owned by Mao Materials. But that's great, because in this photo alone is probably tens of millions of dollars of equipment that we did not have to pay for. But we can use, as long as somebody else isn't using it, we sign up ahead of time, we're nice to the scientist who does own it, things like that. And that way we can monitor not only our bacteria, but also the polymer that comes out of our process, using things like FTIR, DSC, Carver Press, and some other things. I actually don't know what they do. But what we're also working on now is taking that base polymer and coming up with formulations, adding additives to it to make various products. And how we do that is using a twin screw extruder. So this is Joe, one of our research assistants. It is hand-fed, so most of us take turns, have to basically load the polymer into the extruder to a metronome because it has to be pretty precise. This is not a fun job, and we're hoping to get an auto feeder soon, but it's a great piece of equipment. We don't have to pay for it, and we're getting some great products out of it. So we did 30 different formulations because initially we had some interest from the beauty sector to make packaging for makeups or eye creams and things like that, as they want to go more green. And they're doing really great by making the chemicals that are inside of these products more green and transparent, and then they're throwing it in a polypropylene package. And I say, okay, great, here, one step closer. What if that package could also be biodegradable and made of PHA? So we've been working with that. We have a few, not quite cups and jars, or caps and jars, but other prototypes on that front. And while we were doing the 30 different formulations, one of them didn't quite work out so well for caps, but it spun into fiber really nicely. And that's when we decided last October that we would jump into the biopolyester market. And I don't know if you guys realize this, but pretty much everybody in this room is wearing plastic. Polyester. It's an evil, wonderful thing at the same time, because it's a great material. It's in so much clothing, but there's really no way to recycle it right now. So 85% of textile waste ends up in the landfill. Only 15% of it actually gets recycled or repurposed. That's a lot of waste. I think they were saying in San Francisco alone, it's like thousands of pounds a day or something insane like that. So it's pretty scary. So what if your t-shirt could biodegrade once you didn't need it anymore? It could be your favorite shirt. It can get holes in it. You can wear it for many years. Once you throw it away into the landfill or into your home compost, that's when the degradation will start. It's really changing the way people think about fashion. And we've had a lot of interest surrounding sustainable fashion. And I'm excited that I get to go to Europe for a couple of weeks soon to discuss some potential projects with some luxury fashion brands. We'd like to start a little bit higher end so that they can pay a little bit more for the polymer and work our way to the fast fashion, the H&Ms and Gaps of the world. So eventually, everybody's t-shirt could be made out of PHA. But to get there, we needed to take about 20 pounds of our material and we spun it into fiber using a melt spinner. This is a piece of equipment that we partnered with somebody on the East Coast, and they were actually able to spin it into a 19 filament fiber is what they call it. And then we've taken that fiber and used literally off-the-shelf polyester dyes that you could buy at Michael's possibly, and we're able to dye this fiber different colors. And then one of our research assistants, who's not only a good scientist, but also amazingly creative, has hand-woven all of our different swatches and hand-braided all of these different objects that you see here. So she's made bracelets, necklaces, swatches. This is our CEO, Molly. Her and I were invited to a fashion show a couple of weeks ago. Of course, we needed PHA jewelry to wear with our outfits, so Amanda made us a set of PHA earrings. She's been doing some amazing work on top of running all of biology. So she's kind of really versatile. We've also really wanted to understand what is the biodegradation of this fiber? What does that mean? So we were lucky to work with somebody who has a boat on the Berkeley Marina who allowed us to basically put 7 PVC pipes in the water off of his boat, and we came back 8 weeks later and we had some really interesting results. So what you're seeing on the left is actually before the experiment started. The PHA fiber is on the top, cotton is in the middle, and polyester is on the bottom. Now after 8 weeks, that's the same PVC pipe. The PHA and the cotton are both gone, and the polyester is still there. And we were really concerned, actually, we were like, whoa, because we thought it would be a little bit longer than 8 weeks. So we're like, what if it unraveled itself and it's floating around the Berkeley Marina? Like, we're like looking for it, you know, like, oh my gosh. But actually, all 7 replicates looked exactly like this. So we're almost positive that the degradation in seawater happens less than 8 weeks. And so we're repeating this experiment because we missed the window. It was not the best laid science experiment, and we're actually testing them every week to understand weight loss and ultimately when does the degradation occur. So because we are, as I mentioned, a small company, we can only focus on a few things. We've had a lot of interest from the fashion industry, and we really feel like our material could be the t-shirt of the future. Also, we do love the whole beauty story. They're already thinking about transforming the inside, the chemicals and the materials that they're using. Why not the packaging as well? So these are the 2 sectors that we're really focusing on. I showed you a whole bunch of applications earlier. Yes, we could do them all. Eventually, hopefully, we will do them all. But we just need to get to larger scales and a lot more people in order to make that happen. This is the current picture of our team. We're about 15 full-time employees now, including 3 high school interns and 2 to 3 college interns that will happen for the summer. It depends, all different diverse backgrounds like biology, microbiology, engineering, both biochemical and mechanical engineering, chemistry, a few business people. We have a lot of different backgrounds on staff. And while they all went to school for these very specific things, they're all helping us out in all sorts of different areas because we're a startup and we can't hire an IT person. So Carlos, who has his degree in biology, is our IT person as well. And Amanda, who went to school for microbiology, is our prototype, she has something in her title now that's like, and prototype weaver or something, because she's made all these samples for us. Personally, I do a bunch of outreach. I went to school for engineering. I do very little engineering now, but if I needed to talk technical, I could. So being flexible has been really interesting because you just never know what they're going to ask you to do. So where does the future hold for Mango Materials? Well, we've been really successful at the 10 and 20 liters and the 500 liter scale. This year, actually right now, we're currently raising money for our next scale, which will be a 70,000 liter vessel and produce 300,000 pounds of polymer per year, roughly 1,000 pounds a week. We make 10 pounds now. That's really huge for us, but we're really excited about that. Also, then, really what we're going to is the first of its kind commercial plant. And it's going to take a few years for us to get there. But that's when you're producing 10 million pounds of polymer a year. That's when you'll really be able to see products on the market using Mango Materials polymer. And this is what we're envisioning that our first setup looks like. So that, again, this is Silicon Valley Clean Water. Our pilot plant is off in the distance. Our demonstration unit would be about yay tall. And our full commercial plant would be about even bigger tall. And as you can see, we need height more than we need space, which is great in the Bay Area when space is at premium. So we can produce 10 million pounds of polymer from the Silicon Valley Clean Water Wastewater Treatment Plant. If you looked at Oakland, it's 11 times bigger. If you looked at the one in Chicago, it's 20 times bigger. So there's definitely a lot of room for expansion. And after we build the first plant, we will be building replicas of various sizes at methane production sites across the US. And now, if we just took landfills, which we're actually not at right now, but this is a good stat, the amount of methane that's either flared or vented, so not used for anything else, we could produce 3 billion pounds of our biopolymer using methane from landfills in the US alone. So, what does that mean for the whole world? Well, there's methane everywhere. We always say, as long as there's people, there's generally methane. And even when there's farms, there's generally methane. So we could actually expand around the world. So why stop on Earth? We actually have a grant with NASA, kind of bizarre, to explore what our technology would look like in space and on other planets. Because it takes they're anticipating it's going to take about 600 days round trip to get to Mars, and they cannot bring 600 days worth of materials in flight. So they're going to need to be 3D printing plastic on demand. Why not use gases that are being produced in order to generate those materials? And once you're on Mars, why would we pollute that planet like we've already polluted Earth? So we're really excited. It's kind of a wacky out there grant, but we're trying to understand what our technology would look like in microgravity environment. So I really wanted to thank you guys so much for letting me kind of tell you my story, and I wanted to leave you with a few parting thoughts. The first is to don't be afraid to try new things. When I went and got my PhD, I firmly believed I was going to be an academic professor, and I was going to be one of those research, teaching, etc., until I met Molly and decided to change my whole life. It was a big risk, and it's been really hard, but it's also been really fun. Learn something new every day. Like, I didn't realize how crazy the fashion industry really is. I've been reading listening to podcasts and reading articles, and I'm not really fashionable, but you can learn something new no matter what. Do what you love. Life is short. Don't be stuck in something that you don't like, you know. I really love what I do. I love talking to people. I love telling our story. And finally, find ways to see the positive outcomes. This was also for my team a little bit, because we've had a few stumbling blocks lately, and they're all like, oh, this experiment didn't work. And I'm like, what do you mean it didn't work? We found out X, Y, and Z. They're like, but it didn't work. And I'm like, sure, but if you spin it, it can always come out as positive. So find ways to see positive outcomes both in your experiments and in life. Thank you very much.
Not biodegrade in the washing machine?
Yeah, so from what we're understanding, which there are specialized tests for laundering that we haven't got to yet, but will do in this process, but there isn't the microorganisms that trigger that degradation in your laundry. If there was, it would be very dirty laundry. So it shouldn't happen. It shouldn't happen in the laundromat, and the way that the heat profile is as well in the drying process either. So that's that's based on theory, that's what we're imagining. Now the whole putting it into a turbulent environment with soap, we have yet to try, but people have said just off the top of their heads it shouldn't be a problem.
Okay. And also, just random, but how did you guys come up with it?
Oh, good question. So when we started the company, we had envisioned that we would be ultimately making products. We had naively thought that, by year 2, we would be making tons of money and everybody would be buying Mango Materials, fill in the blank. So we really wanted a name that was clean and fresh and memorable and kind of reflected the natural process that we have. I don't think I mentioned it, but we don't genetically modify our organisms. They naturally do this themselves. So we were like, we wanted something natural. Our competitors all had very scientific names, which is totally fine for them, but we did not want our name to end in an X like a lot of them do. And mangoes are our CEO's favorite fruit. So that's how we came up with Mango Materials. Yeah.
At what point will this option become economically possible for a lot of people? Like when will it go from high-end fashion and high-end makeup to something that we would find in everyday stores?
Yes, we need to get to the full commercial scale. So 2020 plus, I guess is what it says on here. And once we're producing millions and millions of pounds, then it becomes economically competitive to produce. So we can drop our price to about $1 a pound or less, which is really what PP and PE are right now. And that's when you'll start to see the markets kind of open up for us. But we're envisioning, within 5 years if things go well. Yeah. Yes.
Are you thinking to co-locate the actual extraction of polymer from the residual bacteria in the same place in the process, and then going into conversion into whatever is in one process?
Yes, even at the demo scale, that will all happen in line. So it does, the bacteria need a certain amount of time to grow the polymer, but that's really the only batch part of the process that needs to happen. So we can have continuous up to then have a batch, but you can do it in parallel, so then you have a multiple batch that can then feed to the whole downstream, including going all the way to formulation. That will all be in line. We're envisioning, bigger facilities will have hoppers where the pellets come out at the end and they go off on a truck or a barge to wherever. Yeah. Yeah, we call it quasi-continuous. Yeah. Yep. Yep. Yes. Yeah, potentially. Obviously, you go big. When you go bigger, your economies of scale are better. There's lots of other things, so we'd love to go big as soon as possible. But there's not a lot of options for some of those smaller methane producers because electricity just doesn't make sense for them. So we want to also cater to that option as well. And then that would probably be more of the case of we produce our caps at this facility, or our t-shirts for this fancy brand happens here, and then we work through the supply chain from there. But if we could go big, that would be even better. You had a question?
Is anyone else doing the exact same thing as you and just how they
Yeah, there is other people making PHA. They generally use sugar as their feedstock. There is another group in Southern California that is taking waste gases and producing some sort of polymer. They're very secretive, so we're not quite sure if they're doing methane to PHA or not. They're definitely not in the fiber space, so we really want to be the first ones to make the biopolyester, and that's fine. Like if they're doing PHA and they want to tackle some other market, that's even better because there's more suppliers. It just helps them push this agenda forward together. So we don't really want to be like, oh, they're bad, we're good. They're just, they would never, well, from what we know, they would probably not be speaking to a group in general. They're very, very secretive in what they're doing behind closed doors. We've tried to find out. We're curious.
How did you decide to focus on microorganisms?
I've always been fascinated by bacteria, and I kind of thought they'd get a bad rap. People are like, oh, bacteria, gross. For my undergrad, I did so much chemistry that I really wanted to completely leave chemistry behind, and I thought, ooh, biology sounds cool. Microbiology is fascinating. There's so much that you can do with it. I mean, we're studying one type of one organism that does one special thing. There's just so many interesting things that other organisms can do. I felt like it opened a lot of doors for me. And and I just wanted to kind of find good bacteria and promote them instead of giving them a bad rap. Thank you guys all so much. Be gentle with a few of them. I talked to 7th graders yesterday, and they kind of demolished some of